And as uh, you might heard from the announcement from the university, we are going to have, I mean, the university decided to extend the online lecture 2 more weeks. That means after today's lecture, we are going to have 2 more online lectures. Not only in this reliability engineering course, but this policy applies to all the courses in the university. So that means we are going to have 2 more online lectures after today's one. So anyway, last time we briefly reviewed why do we need to study this course, reliability engineering. We talked about probabilistic risk assessment and how it is applied to quantitatively estimate the safety of a nuclear power plant. And also, it may be applied to other types of plants and large systems. So today, and also we briefly reviewed uh, very basics of a probability theory, like set theory, and how we calculate the probabilities. And today, we are going to start. Okay. So we are going to start from Bayes theorem. Bayes theorem. It is in section 2.2.3. So first of all, what is Bayes theorem? So, so where should I start? Well, let me open our notebook. P-A-Y, Bayes theorem. So we need this Bayes theorem. Let me slightly enlarge our space. Oh, and we do not need one more S here. So Bayes theorem is necessary to, so when we have a certain belief on things, or when we have a certain probability distribution, and if we receive another new information or another new observation about the fact, then maybe in that case we need to change our distribution or belief on another thing. So Bayes theorem is necessary to change one's knowledge about an event. When we have another new evidence, then it is necessary to change our previous probability or previous belief on something. So let's start from here. Maybe we may go back, or so we are going to first start from probability of, if we have two events, A and E. So the way we calculate this is that when we calculate the probability of, so A and E are all two different events. Like A can be the event of having 1 when after rolling a dice, and E can be having the head when we toss a coin. So the probability that we are going to have 1 from the die and head from the coin can be calculated with probability of first of A and multiplied with let me slightly fix this one. So and probability of the event of E, the probability of event E given event A. So that means this is the probability that A event occurs, and this is conditional probability that event E occurs under the situation that event A also occurred. And it can be also given in the form that probability of E multiplied with probability of event A occurs given event E. So if we take these two, then the probability, so if we move this probability A to the right hand side, then so this form is very simple. This is the simplest form of Bayes' theorem. Or of course it can be written in, if we have some consistency with our textbook, then probability of our textbook, we want to calculate probability of A. So we are going to divide, move this term to the right hand side, and then place it here. So if we know the probability of the occurrence of A and probability of the occurrence of E, and we know this conditional probability, then we are able to calculate this conditional probability, A given E. So that's the very essential part of Bayes' theorem. So it is necessary to change our knowledge or our belief after we observe another event. So in this case, this part so probability of A probability A is called as prior probability. So before we observe some event, before we observe event E, and the probability after this is called as posterior or probability. So this is the probability, also this is the probability A, but after we observe this event E. So if we go back to our textbook, so we just followed this, and this is what is called the simplest form of Bayes' theorem. And if we have many events and different events, then it can be given in a different form. Also, I already told you that this is called as prior probability. And after observing the event or evidence, then this is called as posterior probability. So where can we utilize? So instead of that, let's briefly review this example 2.7. So what does this mean? So from example 2.7, so that there are 70% of inventory comes from vendor 1 and 30% from vendor 2. So this factory receive 70% of their memory chips from vendor 1 or another from factory 1 or another 30% from factory 2. And the two vendors have different probability of having defects. So in case of vendor 1, 99% of chips are okay, but that means 1% of chips will have some kind of defects. In case of vendor 2, 88% will be okay. That means 12% of the chips will have some defects. So these are all basic information that we have. So A1 indicate that the event of chip A, the event A1 indicate that the chip was supplied by vendor 1. A2, the chip was supplied by vendor 2. And this E event indicate that the chip has some defect. So what does this mean? Probability or the event E happens given A1. That is, the event E is defective given it was provided by vendor 1. And you may see this probability that, so probability of E, so probability of the probability that a chip is defective given the chip was provided by vendor 1 was that previously it was mentioned that the 99% of the chips provided by vendor 1 is okay. That means 1%, 0.01 have some defects. So this becomes the conditional probability that a chip is defective when it was supplied by vendor 1. Similarly, this would be the probability that a chip is defective when it is provided by vendor 2. And its probability was 0.12. So because 88% was okay, that means 12% will be defective. So we have these probabilities. So what can we do with what we can do with the Bayes theorem is that this. So when we found a chip, when we found a defective chip, then we would like to know whether that defective chip come from vendor 1 or vendor 2, or the probability that the defective chip that we just found came from vendor 1, and the probability that the defective chip came from vendor 2. So, what you should know is that this is the probability that a chip is defective given the chip was supplied by vendor 1. And what we would like to know is that given a chip is found to be effective, this is what we call as observation. So we already know that this chip is defective. Then the conditional probability that, so given the chip is already defective, then the conditional probability that it came from vendor 1 was calculated by using Bayes' theorem. So if we go back to our notebook, so what we just did was that, another thing that we may say is that so in our previous example, if we apply, if this is the probability that the chip was produced by vendor 1, then all these probabilities will be given. The probability that this is a kind of defect, the probability that a chip is defective. So with this all data, we are able to calculate that after observing a defective chip, we could find the probability that defective chip came from the vendor 1. So maybe it may be a little bit confusing. Let's slightly go back to our example again. So previously it was said that if we select one chip, then maybe with the probability of 0.7 or 70%, it came from vendor 1, and with the probability of 0.3, 30%, the chip came from vendor 2. So that was our something called a priori probability. So, and that chip can be defective or not defective. So we don't know whether it is actually tested or not before it is actually tested. But after testing, before testing, we do not know whether it is defective or not. But after testing, we found that the chip is defective. That means we achieved a new knowledge, a new information about the chip. So before the test, we did not know that. After the test, we found that the chip was defective. It is a new information, new knowledge. And the new knowledge can be utilized to our probability kind of a distribution that, so after it is found that the chip came from the vendor 1, if after finding that the chip is defective, then now previously the probability was 0.7. The probability that the chip came from vendor 1 was 0.7. That is a priori probability. And with the knowledge or with the observation, with this new information that the chip is defective, then after that new observation, the probability that the chip came from vendor 1 now changed to 0.163. So we had this new information. The chip was defective. And that knowledge or that information can be used to update our knowledge or our belief or our distribution, probability distribution, that the chip came from the vendor 1. So as I told you, when you go back, so in that sense, so this Bayes theorem, it changes our knowledge about an event. So in this case, the event was that the chip came from vendor 1. In light of new evidence, the new evidence was that, so after test, the new evidence was that the chip was defective. And after knowing that, before knowing that, this probability was 0.7. But after knowing that, or after observing, after receiving that new information, the probability is now changed to 0.163. So Bayes theorem can be used to update our knowledge or change our knowledge after we receive new information. So it is a little bit, the concept is a little bit, maybe a little bit difficult to understand, but it is very important concept in dealing with a lot of probabilistic analysis. So another example that this Bayes theorem is utilized is that we want to know some probability of some component failure. So we do not have a lot of experience. So like 20 or 30 years ago, or in Korea, when we first started Gori 1 nuclear power plant, we do not know how often components will fail. So we did not know that. So all we could do was to receive some failure data from other countries like United States or Europe. And then that is our knowledge about the failure of those components. And as we gradually operate the nuclear power plants, we gradually accumulate our own data. And that will be different from the data that we received from other countries. And in that case, such new data accumulated in our country, or new data or new evidence utilized to update our knowledge or update the data, the failure data of the component. So new information is utilized to change our knowledge. That's how Bayes theorem is used. So I hope you also try to solve another example problem related to other there are two more example problems, so that you have a very clear understanding on what Bayes' theorem is. So I'm going to move on to section 2.3. 2.3, from now on we are going to see many probability distributions. So section 2.3 is about probability distributions. Probability distributions. So to do that, to talk about probability distributions, so section 2.3, we need to first talk about a new concept called random variable. So in short, it is denoted as RV. So maybe students may, when you do some computer programming, then you utilize some variable. So when x equals 3, then x becomes maybe okay, so this is our MATLAB environment. So when you put x equals 3, x is a variable. X is a variable. And in this case, x is always 3. We do not have any question about that. But this concept, random variable, is some kind of n. Also again, in this case, x is always 3. The outcome of x would be always 3. So let's go back to our textbook. So random variable. So we are going to first talk about random variable. So let's consider an event with a number of possible outcomes. So when you talk about a variable, it had a fixed outcome. When x equals 3, then x is always 3. But in case of a random variable, it may have a number of many different outcomes. So one example is that so when you roll a die, then you may have the outcome of 6 different outcomes. And for all 6 outcomes, you have probabilities associated with that. So this would be x, small x. The probability that x becomes small x. So the probability of having 1 after rolling a die would be 1 over 6. And also 2 will be same. 3, 4, 5, and 6. So what is important here is that let's write it as x, capital X means the number after rolling a die. I'm sorry. And here x is a random variable. And this x, capital X, has 6 different outcomes. Not only one, in this case, 6 may have, capital X may have 6 different outcomes. And for each outcome, this is the case when this is the probability that capital X becomes 1. That is 1 over 6. And also, the probability that capital X becomes 2 is 1 over 6, and so on. So as you can see, a random variable may have many different outcomes, and probabilities or probability distributions will be associated with those possible outcomes. So that is basic concept of random variable. So a random variable may have discrete, or it may be continuous. So in this case, it is this random variable have the outcome have a finite number of outcomes which are not continuous. In this case, the random variable x is a discrete random variable. So let me add discrete random variable. Maybe another example. T, capital T. If capital T indicate the survival time or the time to failure of a component. So after you purchased one component, or after you purchased your cellular phone, then some failure may occur. Maybe in a quite short time, like after you may experience some failure after just 1 month. It may be 2 months, or it may be any time between 1 month and 2 months, or you may use the cell phone without experiencing any failure for a long time. Like the time to failure is maybe 5 or 6 years. So in this case, t is also a random variable, but in this case it is going to be a continuous random variable. So t is the time or the survival time, the time until any failure occurs of a component. And it may be a very short time, or it can be extended to a quite long time. So we are going to deal with these two different types of random variables, discrete or continuous. And After that, some basic discrete. So we are going to talk about some distributions. Of course, rolling a die, in case of rolling a die, we also have this distribution. And maybe we are going to think about other types of distributions. Or if we kind of visualize that. So with this trap, we are going to use some example. So x equals 1 to 6. So we are going to have 1, 2, 3, 4, 5, and 6. These are the outcome after rolling a die. And their associated probabilities would be 1 over 6, 1 over 6, 2, 3, 4, 5, 6. So in that case, let me show you again. So once again, x, y would be, so we are having this probability distribution, and we are also able to see some graph on this. So for all cases 1, 2, 3, 4, 5, and 6, we are going to have the same probabilities. Also, this is a probability distribution. So first we are going to see some important properties of discrete probability distributions. So first, all probabilities will be bigger than 0. In case of rolling a die, we are going to have x 1, 2, 3, 4, 5, and 6, and their probabilities will be greater than or equal to 0. And their probability sum of their probabilities will be 1. Of course, the probabilities of all possible outcomes will be 1. And this is the kind of something called cumulative distribution function. So the probability that some capital X is smaller than X. So when we go back to our rolling a die example, maybe this would be. So probability that X maybe probability that X is smaller than or equal to X. So probability that here it is the probability that the outcome will be exactly X. That is all 1 over 6. This is the probability that the outcome X is smaller than the number here. Smaller than or equal to this number. So smaller than or equal to 1 would be 1 over 6. When X equals 2, the probability that the outcome the outcome is smaller than or equal to x, in this case 2, would be 1 over 6 and 1 over 6. So it is going to be 1 over 3 or 2 over 6. When this capital X, when this lower x is 3, then the probability that the outcome is smaller, this outcome is smaller than or equal to this small x3 is that is all the cases when we have the outcome of 1, 2, and 3. So that is 3 over 6, and so on. So 4 over 6, 5 over 6, and 6 over 6. So it is a kind of cumulative distribution. So these probabilities are gradually accumulated. And if 6 is the final element, then the final probability should be 1, because sum of all probabilities should be 1. So if we go back to our textbook, so that is denoted as f of x, and it is called as CDF. CDF means cumulative distribution function. So so this let me write that down in our notebook. So some basic cumulative distribution function is usually denoted in short as a CDF. And this probability is used here, and it is usually denoted as f of x. So it is a function of x, where the probability of random variable x is all smaller than or equal to this lower letter x. So go back to our textbook again. So we have several examples of discrete probability distributions. The first one is the discrete uniform distribution. By uniform, it says that the probabilities are all equal. So if the samples, we have k elements, then the probability of each element becomes just 1 over k, because all k elements should have the same probabilities. In case of rolling a die, we have 6 elements, and the probabilities will be 1 over 6. Yes, we have that example here. So when rolling a die, rolling a die is, so after rolling a die, we have the probability distribution that we get is exactly an example of discrete uniform distribution. So because you understand the rolling and the probability distribution of rolling a die, you will not be you will not experience difficulty in understanding this. So after that, binomial distribution. I wonder whether you heard of this name or not, binomial distribution. So basically this bi indicates that there are only 2 things. So in this case, we are going to consider a trial, or consider a case when there are only two possible outcomes. Tossing a coin would be one example of this. We are going to have either head or tail. In that case, of course, the probability will be usually equally 0.5, but maybe there are other kinds of examples where the probability of one event is p, and then probability of the other event would be 1 minus p. So, and then and then we are going to do n independent trials. In case of tossing a coin, we are going to toss the coin n times. And of course there are some event that we are interested. That is called as a success. So if we are interested in having the head position or head face of a coin, then after tossing 10 times, and maybe we are interested in how many times we are going to have the head face. On average, of course, 5 times are expected, but if you are very unfortunate, you will have much less times, like 4, 3, 2, 1, and even after tossing 10 times, it is also possible that you will not have any head position or head face. So it have a kind of a probability distribution. And of course this number should be a non-negative integer because it indicates the number of trials. In that case, the probability is given. So the binomial distribution. In fact, we had discrete, previously uniform distribution where all the probabilities are equal, and binomial So when we talk about binomial distribution, there should be only two possible outcomes, and its probability is calculated as the probability of capital X becomes a small x. So here this x is a random variable for the number of in this case number of successes. So if the as I already told you, if singing the head face is the success, then it is going to be the number of singing the head face. So how can you calculate this probability that we are going to have? Like, so for example, so Okay. So probability of x equals x. What would be the probability in that case? And P indicates probability of success. So P is the probability that we are going to see the event that we are expecting. And also N is number of trial. So if we toast 10 times, then the number of trials will be 10. So in that case, in such cases, what would be the probability that we are going to see 0 successes? That means we are going to see all failure events. I hope. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the probability of seeing 0 success, maybe the probability of seeing the probability of seeing 10 successes would be much easier for you. So that is going to be the probability. In this case, it is going to be probability of, because we need to have 10 successes. So in that case, what would be the probability that there would be 0 successes? In that case, all trial should fail. So the first trial should fail, the first trial should fail, the second trial should fail, and so on. So the probability becomes 1 minus p. In the second case, if the probability that we are going to have just one success would be 1 success and then 9 failures. What about when we have 2 successes? Then 2 successes, 8 failures, but there are many combinations for that. How many combinations are we going to have? So among the 10 trials, we need to have 2 successes. And such cases would be such cases would be 10 combination 2. So it is going to be 10 combination 3, 4, and so on. So we may be able to generalize this. So when there are n trials, and if we want to know the probability of x successes, that is going to be x successes, x number of successes, and the remaining m minus x failures, while there are n combination x, so nx combinations for that. So let's go back to our textbook. So that is the so so let me show you one example for that. Binomial distribution. So we need to have a probability. If the probability is 0.5, that is the probability of tossing a coin. And if the number of trial is 10, then, and also your x becomes the worst case, we are going to see 0, and the best case, we are going to see 10 successes. And this MATLAB MATLAB is very useful in so MATLAB and binomial. If we do the search, then it tells you how binomial distributions can be described. So it gives us all the descriptions about binomial distribution, and it tells us that we have binomial CDF, binomial PDF, and so on. So in fact, what we need is this function here. So binomial distribution, and x is the number that we are expecting, n is the total number of trial, and p is the probability of success in each trial. So by using so with this information, y can be calculated as a binomial PDF. So we are going to apply x, and total number of n and p are total number of trials and probability of each success. And x and y will give us this type of distribution. So of course we have in 5 we have, so there are small, very small, but probabilities of having no success. And of course the 5 times it has the highest probability when we observe 5 successes out of 10. And also we have the probability that there are 10 successes out of 10 trials. If we change the probability, so if the probability is somewhat different, like 0.3, then we are going to see somewhat different distribution. And if we change, of course, the probability, then we are going to see another different probability distribution. So this is what is called as binomial distribution. So let's go back to our textbook. So we have examples that you are able to study. Another example of discrete probability distribution is something called the hypergeometric distribution. So hypergeometry distribution is associated with a finite population considered in this book. So first, if you read the textbook, then we are going to consider n, the population, finite population of n. So total population is n, and among which there are d items of interest. So there are two different kinds of items, and or there are some a portion of items we are quite interested in. So as an example, we produce the n number of components, but among them the components are defective. So in that case, when we take out n items out of capital N items, what would be the probability that we are going to find X defective items? So maybe if we draw a figure, then so let's assume that this is the population, capital N. So there are n number of population. Among them, we have another. We are interested in d number of items. A small portion of item. We are interested in a small portion of the items. And so the question is that when we what about this? So when we take out small n number of items, then how many defective items or how many items of interest will be included in these n items? That is the question. So let's put it here and also put it here. So how can you calculate that? So the next one is hypergeometric distribution. And we are interested in finding the probability for such cases. And so in this case, we are going to consider the total number of cases. That's what probabilities are. So the number of cases of our interest over total number of interest. That is what we are going to calculate. So first, what would be the total number of cases? So we have a total capital N items. We have capital N items. So we are going to select small n number of items out of capital N number of total items. So that is total number of cases of taking or selecting small n number of items out of large capital N number of all the population. So this would be all possible cases. So what would be the cases of interest? So we need to select. There should be n defective. There should be. We are interested in first. There are d items of interest. Out of that, we need to take x. So first, we need to take x items of interest, and then after that, we need to take out of these are capital N minus D would be the number of cases that are not defective or that are not in our interest. And then here, how many items should we take out in this group? Total, because we are going to take in total n items, and x items are already taken out in the group of interest, and n minus x should be taken out. So that's the equation for hypergeometric distribution. Of course, in MATLAB we have the function for hypergeometric distribution. So for example, if we have 100 items, out of that we have 10 items of interest. If we take 10 items, then what would be the number of items of interest? What would be the possible items of interest out of 10 withdrawn items would be from 0 to 10. So no items of interest to all 10 items of interest. And then y is going to be, so once again, so once again, we are going to MATLAB and hypergeometric function, and we have a PDF here. So the PDF, its syntax is a hypergeometric PDF, and we need to insert x total number of interests and the number that we take out. So hypergeometric PDF, x is the number that we are in, x is the numbers that we want to calculate the probability, total number of interest, and then the number that we take out. And after that, we may draw a bar graph. and this would be, so in this case, the probability of zero defect, and of course the probability of so out of 10 there are only one item of interest. That probability has to take out 0. We do not take out any item of interest. Or maybe there are 2 items of interest, 3, 4, and so on. Of course, even 10, we have very small, but still we have some probabilities. To know that, so these are the numbers, the number of items of interest, and this is the probability distribution. And of course, in the probability that we take out all 10 items of interest is still exist, even though it is a very small value. Lastly, there are one more discrete, not one more. We need to explain Poisson distribution. That will take some time. So at this point, I would like to take some break until 4:30. So we are going to have a 15-minute break. So before taking the break, I would like to check the attendance of our students. So please leave your name in the chatting window so that I can check your attendance. And after that, we are going to take 15-minute break, and we are going to restart this lecture from 4:30. We are going to restart our today's lecture. So today we briefly talked about first Bayes theorem, and after that we are going and also explained the basic concept of random variable, and then we started to explain some discrete probability distributions one by one from discrete uniform distribution. So discrete uniform distribution, and then we have a binomial distribution and hypergeometric distribution. And the next distribution that we are going to talk about is this Poisson distribution. So hypergeometric, and then Poisson's distribution. So this distribution, so first this model assumes that objects or events of interest are evenly dispersed at random in time or space domain with a constant intensity lambda. So in that case, this random variable x is the number of failures observed, or the number of events observed at a process plant during a year or something. So in that case, x follows Poisson distribution. So maybe another example. So we are going to go back to our notebook, and then next one is Poisson distribution. So to describe Poisson distribution, First important assumption is that constant rate in time domain or intensity in space domain. So a widely used example is the number of cars visiting a gas station. So if there is a gas station which opens like 10 hours a day, and every day they receive like 50 cars, then on average, the number of cars visiting the gas station in 1 hour would be just 5 cars. So that example again. Maybe I can write that example here. So we get in a gas station, 10 cars, 10 open hours. Let me write down 50 cars visited in 10 hours, 10 open hours. Then that means there are going to be about 5 cars on average, 5 cars per hour. That is an average value. Then x, a random variable, that means for the number of cars visiting in an hour, not in an hour, in so not on average. It is if we first, if we specify just 1 hour in any arbitrary time, and we know that on average 5 cars will visit on average for an hour, but maybe it is a kind of random behavior. Maybe less than 5 cars, maybe 4 cars may visit the gas station, or 3, 2, or even no car visited at all for just 1 hour of time period. So it all has some probability distribution. And theoretically, this distribution can be derived from the binomial distribution, and n goes to when the number of trier approaches infinity, and probability approaches to 0, while the expected number so expected number, that is denoted as in our textbook rho, equals MP. and this is simply a constant. So with these assumptions, the Poisson distribution can be actually derived starting from a binomial distribution. And here the probability distribution is given in such a way that so here we have x factorial and rho to the power x and exponential minus rho exponential minus rho. So it has this probability distribution. So let's go back to our textbook, and then here rho is the only parameter of the distribution. Only single parameter is used in Poisson distribution, and x would be the number of events that is observed in a non-random time interval, and rho would be lambda t, where lambda is the rate or intensity. So in our example, so if we go back to our note, then this would be lambda. This is the rate. In this case, in the time domain, this would be we have this constant rate in time domain, and the constant rate is that 5 cars visit each hour. So the visiting rate would be 5 cars per hour. And in this case, on hour, so that means t equals 1 hour in this example. And then in this case, rho would be the expected number, rho would be lambda multiplied with t. So that means the expected number for an hour would be simply 5 cars per hour, and if we are calculating on the expected number for an hour, that is going to be 5 cars per hour, 5 cars. If we are interested in the number of cars in 2 hours, then of course in that case the expected number will be 10 cars for the 2 hours. So in that case, rho would be 2. Not 2. Rho would be 10. So let's go to the MATLAB one more time and see another example for Poisson distribution. So in this case, the lambda is considered as 5 cars per hour. So this is for lambda, and t, let's just for 1 hour. It is for time duration. In the case, rho would be lambda multiplied with t. So this is for rho. That is the expected number. And we are going to use this rho or r in our equation. So the x would be, there can be 0 cars visiting for the hour, and maybe what would be the maximum number of cars that visit during 1 hour. In fact, for the 1 hour there can be almost the infinite number of, even though the probabilities are small, infinite number of cars visiting for just 1 hour. Simply, their probabilities are very, very low, almost ignorable. So let's consider the number of cars up to 20. And y is going to be, so for Poisson distribution, POSS, PDF is the function that we are able to utilize. That we are able to utilize. POISS, PDF. So x would be the number, and in fact, not lambda, we need to provide rho. And so this would be the distribution of the probability distribution for the number of cars for the next 1 hour, for say. So of course we have a very small but probability that no cars visit for the next 1 hour, and 1, 2, 3, and what we can see is that the probability of visiting 4 cars and 5 cars are same, almost the same. We are going to check that. And as the number of cars visiting for the hour increases, and their probabilities gradually and significantly decreases. And in case of about 20, the probability of visiting 20 cars is very, very small. So maybe in fact we are actually conforming those numbers. So these are x and these are probabilities, and 0, 1, 2, 3, 4, 5, and the probabilities for the probabilities for 4 cars visiting and 5 cars visiting are almost the same, and 10 cars, 20 will be very, very small, 10 to the power minus 7. And of course this can be extended to 100 or 1000. Let's try. Just their probabilities will be very small. So the probability of visiting 100 cars for the next 1 hour would be 10 to the power minus 91. So the point is that it is also possible. Simply, their probabilities are very, very low. So in this way, Poisson distribution can be used. So this was the example that we just dealt with, the gas station and the number of cars visiting for the next 1 hour. So Poisson distribution can be applied to such examples or such situations. After Poisson distribution, next would be geometry. Geometric distribution. So geometric distribution is the number of so Bernoulli trials. That means so a Bernoulli trial indicates that a trial that have only two outcomes, even success or failure. And if it is assumed that if we do that trial again and again until we eventually see the success event. So that geometric distribution give us, so maybe some lucky person may succeed in his or her first trial. Maybe next time the second trial. If he or she is very unlucky, then maybe 5 or sometimes 10 trials will be necessary to eventually see the success. So geometric distribution, the random variable for geometric distribution is to represent the number of Bernoulli trials to get just one success. Then how can you calculate that? Of course, x is the random variable for the number of trials to get one success. So if the success probability is p, then first it needs to fail. So if we want to calculate this geometric distribution when x equals 5, then there should be 4 failures prior to the fifth style, which will turn out to be a success. So the general rule is that we need to fail x minus 1 times, and then in x time we succeed. So this would be the distribution for geometric distribution. And x may go on and on and on. It can be extended to infinite number. So now let's go back to let me give you some example for that. So geometric distribution. So let's think about the case of tossing a coin. Then x can be extended from 0 to, let's consider until 10 trials. Okay, of course, this can be much bigger value, bigger numbers. Then y would be geometric distribution, and the material function for geometric distribution is GeoPDF. And x and the probability X and Y will give us this type of I need to I'm sorry x equals 0 does not make sense, so x should start from 1. So the probability that the trier, I mean, well, geometric PDF. Let me recalculate this. In fact, I am expecting 0.5. 0.5 for the probability that after tossing a coin, we receive the success in the first case. Maybe later we need to check that. The distribution we are utilizing, I mean the form of distribution is somewhat different. So it is found that it returns the probability density function of the geometric distribution at each value in X using the corresponding probabilities in P. And well, so this is the description. Details. So what it calculates is that instead of nth trial, so before success, so the random variable x here indicate the number of so-called failures before eventually observing the success. So the equation is slightly different here. So instead of x minus 1, we have x, and x starts from 0. That means no failure, and one failure, and in the second trial, we observe the success. So and so on. So it is found that the equation, I mean the equation used in MATLAB is slightly different from, or the definition of geometric distribution used in MATLAB is slightly different from the one that is described in our textbook. So here, so if we would like to use the geometric function in the MATLAB, it should be like this. Or if we just simply define the function yourself. So first, so in this case, so 0 failure, 1 failure, 2 failures after observing the success. This is the case when we utilize the function in MATLAB. Of course, we are able to, instead of utilizing the function in MATLAB, we may define function ourselves. So if we use the definition in our textbook, the probability will be p multiplied by 1 minus p times x minus 1. Let's find out whether we are use this from x minus 1. Okay. So in this case, if we use the definition of geometric distribution in our textbook, and if we develop our own function, then in the first trial, probability 0.5, second trial, third trial, and so on. So the success in the 10th trial would be almost 0.1%. So this is an example of a geometric distribution. So we just finished all the examples of geometric distribution. We already covered the part and also covered the geometric distribution. And we are going to start continuous distributions. For those students who studied or who took courses on already, so let me show you some examples. So for example, so chi, that is the energy distribution of fission neutrons. So chi e, dE is the fraction of fission neutrons with energies between E and E plus dE. So this was also an example of continuous probability density function. Of course, we are going to also see what a probability density function is. And also, this would be probability density function for Maxwell-Boltzmann distribution. These were the examples of continuous probability density functions. So, some basic continuous distributions. So now, instead of discrete random variables, we are going to deal with continuous random variable. So one example is that if t represents the time interval within a given emergency action is performed. So, for example, the time to take some action in an emergency situation. So that means that the time can be very short if the pilot is very experienced. So it can be several seconds or less than several seconds. Or if the pilot is not that experienced, then it will take some more time, like 1 minute or several minutes. It can be much longer than that. The time will be much longer than that. And in that case, we do not have a clear point, or in case of rolling a die, we could have a discrete number of set, number of space. Like in case of rolling a die, we could have 1, 2, 3, 4, 5, and 6. They were the that was the universal space. But in this case, we are going to get only a real number in a continuous time interval. So the point here also is that if we utilize such continuous random variable, then the probability of exactly one point, one time period will be 0. We cannot define probability in that sense. The only way we can define the probability that the time is between exactly 2 minutes, then it's not possible. The probability that the time to action lies in 2 minutes. So we are able to define such probabilities. And to describe this type of the distributions, for continuous random variables, we are going to first define CDF. And then define PDF. PDF is probability density function. So let's go back to our notes. Some basic continuous distributions. Two point 3.3. Some basic continuous distributions. PF distribution function, in short CDF. So we already defined the CDF previously. So usually CDF is denoted as f of x. That is the probability that this x, or in our example t, so depending on what kind of what letter we used to define the random variable, so that exactly sometime t would be 0 always, but we are able to define the probability that this is a smaller, the random variable t, or in the example of the pilot performing the emergency action, the time to such emergency action is less than another time of interest. So this is basically function of t. So the probability that the time of such emergency action is smaller than the time of this function. And after defining CDF, we define probability density function, in short PDF. And PDF is usually denoted with smaller f, so that is dt. Derivative of CDF with respect to time, or not only time, with respect to the variable that we are dealing with. And it should be noted that in CDF, D indicate distribution, while in PDF, D indicate density, not distribution. So we do not have a word like a probability distribution function. Of course, in case of discrete distributions, we are able to utilize that word. But in case of these continuous distributions, we don't use probability distribution functions. We don't have such term. So PDF indicates this density function. So with this relation, of course, we are able to calculate the CDF is calculated as integral. It depends on the time. It depends on from which time point this function is defined. So f, we are going to introduce another parameter like t prime. Or in the textbook, maybe we are able to, we may define another parameter called psi. So this would be the definition of cumulative distribution function and probability density function. And let's go back to the textbook. So with this, so cumulative distribution function when t approaches to minus infinity would be 0. And when t approaches to infinity, this function will approach 1. I think we should erase this one. So this is just one typo. Probability that, the cumulative distribution function when t approaches to infinity is 1. So just delete this negative sign. T and between well, another typo here. So this is not infinity, this should be simply t. So let me rewrite all these equations in the here. So with this, some properties are so these are all properties related to PDF. So minus infinity should be 0. So of course this indicates the limit when t approaches to negative infinity. For positive infinity, in fact, that means probability from minus infinity to positive infinity, and this would be same with 1, and in between t would be, this one should be t, and this value should be between 0 and 1 and 1. And some probability should be calculated as the probability of locating between 2 points. So that means, our note, some probability is defined that the probability of locating between 2 time points, like A and the sign of less than or equal to will not be significantly different from just less than, because the probability of exactly time b will be 0 in case of continuous random variables. So probabilities can be defined in this way. So this would be, maybe here we are able to use just t instead of so b, so this would be the probability, or so when we calculate the probability that this random variable t belongs to between a and b, that probability should be in fact calculated by the integral from a to b of the probability density function. And of course this will be same with negative minus from negative infinity to a, and by definition they are same with fb minus fa, so the cumulative distribution. So the probability can be the probability that a random variable is located between a and b can be calculated by subtracting CDF for b, by subtracting CDF for b with the CDF for the time point a. So these are how we utilize, so very basic, how we utilize continuous probability distribution, probability density functions, and continuous cumulative distribution functions. And from now on, I'm going to give you some examples So the first one is that our textbook. So you have example to give you some understanding on basic properties of continuous uh, probability distribution, probability density functions. The first example would be normal distribution, and most of you are somewhat familiar with this function. You could see there are many. I mean, this normal distribution is widely used in statistics, and it is also called as Gaussian distribution. And in fact, this distribution can be derived from the sketch. If you know just one property, that so normal distribution. So so I'm not going to explain all the details